Hi, welcome back to educator.com. Today we're going to talk about the properties of logarithms. In the previous lesson we introduced the idea of a logarithm, which was defined as log base a of x equals y for a to the y equals x. So the logarithm of a number is what we would have to raise the base to get the number. So log a x equals y means a to the y equals x. It's a little bit of a complex idea the first time we talk about it, so the previous lesson's really useful. If you haven't already watched the previous lesson, Introduction to Logarithms, I'd really recommend you watch it because that will get you a grounding in how these things work. It'll really explain things if it's confusing here. Previously, when we investigated exponentiation, we found all sorts of interesting properties, such as x to the a times x to the b equals x to the a plus b, that we could add exponents, or that x to the negative a equals 1 over x to the a, that we flip when we have negative exponents. Since logarithms and exponents are so deeply connected, right, we've got this idea that log of something equals this other version in exponent world, so they're deeply connected, we might expect logarithms to also have some interesting properties. Indeed, they do. This lesson will be all about looking at the properties of logarithms. Let's just start off with some really basic properties. Remember, this is the definition that we'll be working with the whole time. Really good idea to understand this. So from this, we can immediately see two basic properties. Log a of 1 equals 0 because a to the 0 equals 1 for anything, right? That was one of the things we figured out when we were working with exponents. And also log a of a is going to equal 1 because a to the 1 is just equal to a, right? Because it's just 1a. So two basic properties that we get just from the simple definition. Next, we can talk about inverses. Logarithms and exponentiation are inverse processes. If they have the same base, they cancel out. They cancel each other out. This is clear when a logarithm acts on exponentiation. If we have log base a of a to the x, then we're going to get x out of it. Because by the definition of a logarithm, the number that we need to raise x to, right? What do we have to raise a to get a to the x? Well, that's going to be a to the x, right? So a as our base for the right side, a to the x is equal to a to the x, so log a of a to the x equals x, right? It cancels out. Logarithm on exponentiation, they cancel each other out because we've got an a here and an a here as bases, so they knock out and we're left with just the x that we originally had. So logarithms cancel out exponentiation if they're at the same base. We just get left with the exponent at the end. To see the reverse process of exponentiation canceling a logarithm, we first need to realize a useful idea. Notice that for any exponent base, where a is greater than 0, or exponent base is positive, and it's not equal to 1, and any number x such that x is a positive number, there exists some real number b such that a to the b equals x. In other words, through exponentiation, this a to the something, we can get to any positive number, x, right? For any positive number, you say 58 as your x, then with my a, I can raise it to something that will get it to 58. And then if we want, we can name the exponent that will do this. And we called it b here, right? There's some number b such that a to the b equals x. So for example, we could say 10 to the something has to be equal to 100. Our question is, what number is it as our something? 10 to the what equals 100? Well, it's going to be 2, right? We raise 10 to the 2, 10 squared, we get 100. So in this case, our b, if we want to name the number in the box, our b was 2. We could do this for something else. We could say 3 to the box equals 47. Now this is considerably more complex than 10 to the box equals 100, right? 3 isn't going to have some nice integer, nice even power that we can raise it to that will spit out 47, but we can know that there's got to be something that fits in that box. We don't know what the number is right now, but we are confident, we are sure that there's got to be something that we could raise 3 to get 47, so we can just call it b. In fact, if you were to work it out through other stuff that we'll talk about as we go on in this class, if you were to work it out, you'd find out that b is approximately equal to 3.504555. If you plug that into a calculator, you'll see that it's very, very close to being precisely 47. So there is some number out there. We can't get it exactly, but we can get a very good approximation through things that we'll work out on this course. So we can be sure that this number does exist. It is out there somewhere, even if we don't know it. But that doesn't mean we can't talk about it. We can not know what something is precisely and still talk about it as a general idea. So we know this has to be true because every exponential function, a to the something, has a range of 0 to infinity. We've talked about this before, and you can see it in the graphs of it. So since it has a range of 0 to infinity, since any number can come out of it as long as it's a positive number, then there has to be some b that will make that number from between 0 and infinity. So for any x contained in 0 to infinity, for any positive number x, there has to be some b that when we plug it in here, when we plug in b here, we will wind up getting a to the b equals x. We will wind up getting that x when we plug it in. This idea that there's always an exponent for creating any positive number, it won't work if it's negative, but for creating any number is really important. We'll use this fact to prove a variety of properties about logarithms, so we want to keep this idea that if we've got some x and we know we have some base a, then there has to exist some real number b to make a to the b equals x. So you start with a base a, you start with some sort of destination x, you're guaranteed that there is a b that will get you to that destination through exponentiation. With this idea in mind, we can now show inverses in the other direction. Consider a to the log ax. Now, by our new idea, we know that there has to be some b such that a to the b equals x, right? Here's our x, and we just choose the base a. It's going to be connected to the fact that we've got the base a here showing up here. So we know that a to the something equals x, and we're guaranteed that there has to be some b there, so we're talking about it here. We know that there's some b such that a to the b equals x, so we can say a to the log a of, and now we replace it with a to the b equals x, so we replace right here, and it becomes a to the b. So a to the log a of a to the b. Now, we just showed that log base a of a to the b equals b, right? Because logs on exponents cancel out. So log a on a to the b equals b. So we've got the same thing here. Log a on a will drop us down to just having the b. So that b will move over to being the exponent on. We'll have a to the b. But how did we define a to the b in the first place? It was a to the b equals x. So we know that a to the b equals x. Since we created b based on the fact that a to the b equals x, we've now shown that what we started with winds up being equivalent to x, so we have that a raised to the log ax is equal to x. So now at this point we've shown inverses in both directions. If you take log of an exponent, they both have the same base, they cancel out and we're just left with whatever was our power. If we take exponent raised to a log, if we take some base and raise it through exponentiation to a log, and that base there and the base on the log are the same thing, we wind up just having what the log was taking as its quantity. So we've got inverses shown in both ways. We can cancel out in both directions. All right, let's move on to something else. Logarithm of a power. Consider if we had some positive number x and any real number n. Then what if we raised x to the n and took its log? So we had log a of x to the n. By our key idea, we know that there exists some b such that we can write a to the b equals x, right? Same thing. So if we want, we can swap out our x here for a to the b, right? So we've got a to the b now. A to the b to the n. From our rules about exponents, we know that a to the b to the n, a to the b to the n is the same thing as just a to the b times n. So now we've got b times n, or we could write it as n times b. Log a on a to the n times b becomes canceled out because we've got inverses there, since they're the same base, and we're left with n times b. Now, do we have another way to express b? Well, from the beginning, we know that a to the b equals x, a to the b equals x, so we could write that in its logarithmic form, and we'd show that log base a of x is equal to b. So log base a of x equals b because a to the b equals x, right? If we move this over here, a raised to the b becomes x from how we had this originally, so we see that log base a of x is equal to b, which means that we can swap this out, the b out here, for the log ax, and we've got that log ax here. So we started with log a of x to the n, and now we see that we can take this n here and sort of move it out front, and we've got n times log ax. So if we've got an exponent, we can move it out front. Let's look at an example. If we look at log base 3 of 3 squared, by this property, we see that we could take this 2, move it out front, and we'd have 2 times log base 3 of 3. Well, log base 3 of 3, log base something of something, if they're the same something, is just 1, right? What do you have to raise 3 to get 3? just 1, right? So we have 2 times 1, which is equal to 2. Hey, what if we look at the other way? Well, log base 3 of 9, what do we have to raise 3 to get 9? We just have to raise it to 2, so we have 2 here, 2 here. Either way we go at it, we wind up getting the same thing. We see this property in action. Okay, now let's consider two positive numbers, m and n. That should be numbers m and n. Log a of m times n. So log a of the whole quantity m times n. Now, from our key idea, we know that there exists m and n such that we can raise a to the m and we'll get big M, and we raise a to the little n and we get big N, right? So we can swap these things out. We can swap out here and we can swap out here, and we wind up getting log a of a to the m times a to the n. Great. Now, from our work about exponents, we know that a to the m times a to the n is the same thing as a to the m plus n. Same base means that we can add the exponent. So we have log a of a to the m plus n, and then since it's log a on an exponent base of a, we get cancellation once again through inverses. Log a cancels out with that, and we're left with just m plus n. Now we can ask ourselves, do we have another way to express little m and little n? Well, from the beginning, we know that a to the m equals big M. A to the little m equals big M. That was how we set this up. So log of little a to the big M, log of little a of big M equals m, right? Because we know that if we raise a to the little m, we get big M, so we've got that. So we can express it in its exponential form or its logarithmic form. So we now can say, what about looking at it through its logarithmic form? Same thing goes over here with a to the little n equals big N. We can express it instead as log base a of big N equals little n. So at this point, we've got two different ways. We've got new ways to be able to describe m plus n. So we can swap that out, and so log a m here becomes here, and log a big N, little n goes here, right? So you see this here, see this here. So we can swap that out. So what we started with, log base a of m times n, big M times big N, is going to be the same thing as log base a big M plus log base a big N. So if we've got a product, we can split it into a logarithm of a product. We can split it into the sum of the logarithms that made up, of the numbers that made up each part of that product. Let's look at an example to help clarify this. So we could look at log base 10. So log base 10, we'll write it as just 10. Sorry, not just 10. We'll write it as just log, since the common log can be expressed as just log. So log of 1,000. We could write it, if we felt like it, as log of 100 times 10. And then by this rule that we have here, we could split it. We've got a product 100 and 10, so we can split it into log of 100 plus the log of 10. Now, what number do we have to raise 10 to get 100? We have to raise it log of 100. What number do we have to raise 10 to get 100? We have to raise it to 2, right? What number do we have to raise 10 to get 10? We only have to raise it to 1. So 2 plus 1, we wind up getting 3. Alternatively, we could have done this as log of 1,000. What number do we have to raise 10 to get 1,000? 10 at 1, 100 at 2, 1,000 at 3. So we could also see that log base 10 of 1,000 is equal to 3 over here. So it works out either way we want to approach it. So we see now that we can break up products into two different things being added together. What if we took the logarithm of a quotient, log base a of m over n? Well, we could rewrite that as m times n to the negative 1, right? Since we could rewrite m over n as m times 1 over n, and then we can rewrite 1 over n as just its flip, so we'd have n to the negative 1. So we can swap that around like that. From the rule that we just saw, the splitting of products, we can break this as, here's the m, so we have log a m, and here's the n minus 1, so we have log a n minus 1, n to the negative 1. So log a of m, and then we also have our rule that we can bring down exponents, right? X to the n, log of x to the n becomes n times log of x. So we bring this down in front. Since we're bringing down a negative 1, it just becomes a minus sign. So it becomes a minus sign here. So we've got log a of m minus log a of n. Great, big M, big N. Thus, log a of m over n is equal to log a of m minus log a of n. So a quotient becomes a difference. Logarithm of a quotient becomes the difference of the two logarithms. Let's look at an example to help clarify this one as well. So if we look at log base 2 of 32 over 2, well, we could write that by our new rules as log base 2 of 32 is the part on the top, and then the part on the bottom is 2, so minus log 2 of 2. Log 2 of 32, what number do we have to raise 2 to get 32? Well, 2 at 1, 4 at 2, 8 at 3, 16 at 4, 32 at 5. So we raise 2 to the 5th and we get 32, so log base 2 of 32 is 5. What is log base 2 of 2? Minus 1, right? 2 to the 1 equals 2, so just 1. So 5 minus 1, we wind up getting 4. What if we'd looked at it not through breaking it apart, but just simplified it first? 32 over 2, well, we could write that as log 2 of 16. What number do we need to raise 2 to get 16? 2 to the 1 becomes 2, 2 squared becomes 4, 2 to the 3rd becomes 8, 2 to the 4th becomes 16, so this would wind up being 4, so we wind up getting the same thing either way we look at it. Great. Want to caution you, there's no rule for log of m plus n. So notice, none of these properties were ever of the form log m plus n inside of there. That's because there's just no nice formula to break apart log m plus n. So if you've got log of a quantity, and inside that quantity it's something plus something else, there's no special rules. Sorry, there's just no easy way around it. You're going to have to work things out in a complicated way. There's no way to be able to just break things apart or put things together anymore. Lots of people make the mistake that log a m plus n is equal to log a m plus log a n, or that log a m minus n is equal to log a m minus log a n. Those are not true. Not true at all. You can't write them and split them apart like this. These things do not work. It's the same thing as if you have square root of 2 plus 2 saying, oh, I'll just split that into root 2 plus root 2. That does not work, right? You can't just split on square roots. You can't just split on logarithms either. So this idea of just splitting because you see an addition sign, you can't do that. You have to work out what's the logarithm of everything inside of there. There's no clean rules to do that. It's an easy mistake to wind up making, but don't let it happen to you. Be vigilant. Watch out for this. Don't let it happen to you. Don't do the same mistake. Remember, it only works if it's m times n, m divided by n. If it's plus or minus, there's no special rules. You just have to work it out by figuring things out, simplifying, hopefully if you can, like they're actually numbers, but there's really no easy way around it. At this point, we've seen a lot of properties for logarithms, so let's review them. Our base ones right at the beginning were that log base any a of 1 equals 0, because any a raised to the 0 becomes 1. Then also log base a of a equals 1, because any a raised to the 1 is just a. Then we also have our inverse properties, log a of a to the x equals x, that it cancels out when you have logarithm on exponentiation, if they're the same base. And then a raised to the log a x equals x, when we've got exponentiation acting on logarithms, cancels out if they're the same base. Then we have the fact that we can bring down powers, right? If we've got x to the n, log of x to the n, then we can bring the n in front. We've got n times log of x. If we've got log of m times n, then we can split that into log of m plus log of n, right? We've got the two different pieces, m and n, so it splits into log m, log n. So multiplication inside a logarithm becomes addition outside of the logarithm. Log a m over n, log m minus log n. If we've got m here, n here, then we've got this minus sign right here. So division inside of the logarithm becomes subtraction outside the logarithm once we split into two logs. So it seems like a lot of rules, and there are a fair bit of new things that you have to get used to here, but they're all based off of our original definition of what it means to be a log. The idea that log a x equals y means that a to the y equals x. This is really what it is. You can either write an exponential form or logarithmic form. It's just a way of denoting things. So a underneath that y, a to the y, becomes what we were originally taking the log of. And so for any base a, we also figured out this key idea that for any base a, any positive number x, there was a b that allowed us to get to that x. A to the b equals x for any x that we wanted to get to. So these two ideas, you can put them together and you can figure out pretty much any one of these things right here with those ideas. And then these ones are all just kind of coming off of the basic definition right from the beginning. But if you take that key idea as well, you can figure these out. So if you ever forget them on a test, you forget them in a situation where you can't just look them up, you now have a way of hopefully being able to figure them out on your own. They're not quite as easy as being able to figure out all the things that made up our exponential rules, our rules for exponentiation, but we are able to figure these things out on our own. And as you get more used to working with them, get some practice in them, it'll be even easier for you to work them out on your own, and they'll also just stick in your head that much easier. All right, now we're going to switch gears to a new idea. In the last lesson, we mentioned that most calculators only have buttons to evaluate natural log of x and log x, ln x and log x. That is log base e, right? That's what natural log means. And log without a number means base 10. So how could we evaluate something like log base 7 of 42? Well, 7 to the 1 equals 7, and 7 squared equals 49. So we see that there's no easy integer number that we raise 7 to get 42. It's not going to be an easy thing. So we need to use a calculator because 42 is not an integer power of 7. But since it's base 7, we don't have a button on our calculators. What we want is some way to transform the base of the logarithm. If we could transform from log base 7 into log base 10 or log base e, we'd be able to use a calculator because then we have our natural log and log buttons, common log buttons, on our calculator. We can just punch it in. Now, you might have a calculator that lets you just put in an expression like this, but even if you have that sort of calculator, this is still sort of a useful thing to learn. As we'll see in some of the examples, there's ways to apply changes of base beyond just using them to get what these numbers are. And also lots of times you won't have a calculator that is able to do this, and you will only have natural log or plain common log, log base 10, and you'll need to be able to have this change of base so that you can change when you need to take a base that isn't e or 10. To help motivate the coming formula and its derivation, let's look at a specific example. So consider the expressions log base 3 of 81 and log base 9 of 81. So log base 3 of 81, well, we could rewrite 81 as 3 to the 4th, so we see that that's just 4 over here. Now, log base 9, 81, we could rewrite also as 9 squared, so that would be, with base 9, that would come out as 2. So we see that log base 3 of 81 equals 2 times log 9, 81, because, 4 is equal to 2 times 2. So we see that log base 3 of 81 is equal to 2 times log base 9 of 81. And this is somehow related to the fact that 3 squared is equal to 9, right? You square 3 and you manage to get a 9 out of it. Now we can probably intuit that that holds generally. We can figure out that normally, or in fact always, we're going to have log 3x is equal to 2 times log 9x. But let's prove it instead of just assuming. Instead of just getting a feel like, yeah, that makes sense, let's actually prove definitely that that's the case. We start by noting off that x is equal to 9 to the log 9x. Remember, 9 to the log 9x, well, if we wanted to, we could cancel those things out because we've got base of 9 and log base 9, so they'd cancel out, and we wind up having just x, so this here makes sense. But having it 9 to the log 9x written in this funny way, it's a complicated idea, it's hard to see where we pulled it, it's kind of like just pulling a rabbit out of a hat, but with this idea, if we leave it in this form, we'll be able to pull some cool tricks that will let us show what we want to get to. If we want, we can take log base 3 of both sides, right? We know x is equal to 9 to the log 9x, so it must be the case that log base 3 of x is the same thing as 9 log 9x, so log 3 of 9 log 9x, right? We can take log 3 of both of the things on either side because that equal sign means that it has to be equal for whatever happens to it. So log base 3 of x is equal to log base 3 of 9 to the log 9x. Okay, that idea in mind, we can start applying our rules that we have. We know that we can bring down exponents. So in this case, we've got effectively an exponent of log 9x. We actually have it exactly as an exponent. So if we want, we can bring that down in front. So we see that log 3x is equal to log 9x times log 3 of 9. Now, what is log 3 of 9? That comes out to be 2. So we can simplify that as log base 3 of x is equal to 2 times log base 9 of x. And we've proven what we originally wanted to show. We follow a similar structure to create a formula to change between any two bases u and v. So if we start off as x equals v to the log vx, which we know is true because of inverses, then we could once again take a log on both sides, and we'll take log u because we want to get v and u. We want to get both of those logs into action. So we take log u on both sides, and then we can bring this down in front because it's an exponent, and we've got log ux equals log vx times log u v. At this point, we can create a formula that will have log v on one side, log u on the other side. We divide log uv over, and we we swap the order of the equation. We've got log vx equals log ux over log uv. So log base u x over log base u v. Notice that this allows us to change from an expression log base vx into an expression that only uses log base u. Now if we choose our u to be either e or 10 or whatever is convenient for the problem we're working on, we'll be able to evaluate it with any calculator at all, right? Since every calculator we'll be using has natural log and common log, base 10 log buttons, we'll be able to evaluate with any calculator because we'll be able to change out the u's over here. So whatever we wind up having, if it's log base 742, then we can change it into log base 10 of 42 over log base 10 of 42, or alternatively we could have changed it into natural log of 42 over natural log of 42. Both would wind up giving the same thing, and we'll see what it is in the examples. All right, first one, write as a sum and or difference of logarithms, our first example here. So we're working with base 5, but that doesn't affect how any of our properties work. So remember, if we have log of m over n for any base a, then that's equal to log a m minus log a n. So same log base on both, and it splits into subtraction. So in this case, we've got on the top x to the 5th, so we'll have log base 5, same base, minus what's on the bottom, y root z, so minus log 5 of x root, whoops, sorry, not x, said the wrong thing there, y times root z. Great. Now we also have the rule that log base a for any a of m times n equals log base a m plus log base a n. So we can split with addition as well. So we've got multiplication here, right? Y times root z is what's really there. So log 5 x to the 5th minus, now notice we're splitting all of this here. So we're still subtracting by all of it, so we want to put it around parentheses because it is substitution that we're doing here. So we now work on this thing here, log a m, log a n. So our m is y, our n is root z, and we've got log, still the same base, of y plus log, still the same base, 5 of root z. Simplify this out a bit, we've got log 5x to the 5th minus our subtraction distributes, minus here as well, log 5 root z. Now, that is technically enough because we've got a sum and or difference of logarithms, but we can also take it one step further and we can get rid of these exponents. We can get rid of to the 5th, we can get rid of root z, because we also have the rule that log base a for any base of x to the n is equal to n times log base a of x. So in this case, we've got to the 5th, and how can we rewrite root z? Well, remember, root z, any square root, is just like raising to the half. So we can see this, bring the 5 at the front, so we've got 5 times log base 5x. We continue to just bring down our log base 5y minus, we'll rewrite the z, log 5 z to the 1/2. And now we can bring down this as well. Oops, not to there, but we have to move it all the way to the front of the log. There we go. So we've got 5 times log base 5 of x minus log base 5 of y minus 1/2 times log base 5 of z. And there we go. We've managed to write this entirely using very simple things inside of our log, just x, y, and z. We've managed to break up this fairly complicated expression inside of the log into a fairly simple expression inside of the log by just breaking it up into more arithmetic. We can do the reverse, and we can also compact things. So write the expression as a single logarithm. We'll compact all of these log expressions into one tiny log with a more complicated structure on the inside. So first we have, once again, that subtraction becomes division. So 1/3 natural log a plus 2. Actually, first thing, we've got these coefficients out front, right? So we can also bring the coefficients in. So 1/3 can hop up onto an exponent on that a. The 2 here can hop up to an exponent on that b. So we've got natural log of a to the third plus 2 times quantity natural log of b squared minus natural log c. And if you forgot, remember, natural log ln is just a way of saying log base e, where e is a special number, the natural base. Natural log a 1/3 plus 2 natural log b squared minus natural log c. Now we can compact what's inside of those parentheses, because we see we've got subtraction, so that's natural log of b squared over c, right? Subtraction of logs is the same thing as division inside of the logarithm. And now natural log a to the 1/3 plus, well, now we've got this 2, so we can take this 2, and it's hitting a log, right? It's times a log, so it can go up, and it can also become an exponent. So natural log of b squared over c. Make sure we remember that we're doing the logarithm is of that whole thing. So natural log of a to the 1/3 plus natural log, we distribute that, b to the 4th over c squared. And we can also bring this in now. Natural log of addition of logarithm becomes multiplication inside of the logarithm. So a to the 1/3 times the rest of it. So b to the 4th, it'll show up in the numerator, divided by c squared. And we've got the whole thing compacted into a single logarithm. Great. All right. Next one. Evaluate each of the following, use a calculator, and the change of base formula. So remember, our change of base formula, if we have log 742, then we can change to any base, we'll put it as a square right now, of 42, the thing that we're taking our log of initially, divided by log, base has to be the same between here and here. These have to be the same base. And it's going to be of our original base. So since it was log base 742, we now have log of something 42 divided by log of something 7. Right? That's how it works. That's what it meant when we saw log v of x equals log u x over log u v. In this case, for this one, our v is 7. V equals 7. Our u is whatever we are about to choose. So we can make it any u we want. We could make it 50 and it would work. We could make it 0.1 and it would work. But let's do something that shows up on our calculator. So let's choose e, right? So we can put in an e here and an e here. So we'll rewrite that as natural log 42 divided by natural log of 7. We punch that into our calculator, and that will wind up coming out to be, it'll go on with lots of decimals. So let's cut it off, and it'll wind up being approximately 1.9208. Now, if you wanted to, you could have also done this as something else. It would have also been the same as log base 10 of 42 over log base 10 of 7. That'd be the same if you used common log, something that also shows up on a lot of calculators. And you'd wind up getting the same thing. It would come out to be approximately 1.9208. Now, if we want to check our work, right, we want to make sure that that did work out, we would check it by saying that 7 to the 1.9208 does come out to being 42, and it does come out to being approximately 42, so it winds up checking out if we punch that into a calculator. Let's do log pi of root 17. Same basic idea here. We can do it as natural log of root 17 over natural log of pi. We punch that out in a calculator, and we get approximately equal to 1.2375. And if we wanted to, we also could have done that as log base 10 of root 17 over log base 10 of pi, and we would have wound up getting the exact same thing. It would have come out to be approximately 1.2375. Either one you work with, they're both going to wind up working out to give you the same answer. Great. And if you wanted to, you could also check this as well. You could check and make sure that pi raised to approximately 1.2375 does come out to be approximately root 17, and indeed it does if you want to check that this does work. Great. Fourth example, given that log base 5 of a equals 6 and log base 5 of b equals 1.2, evaluate each of the following. So at this point, we want to use the rules that we have to split things apart. Splitting it apart will allow us to use the pieces of information we have, right? We have to see a log base 5 of a before we can swap it out for 6, so we have to get that sort of thing to show up. Same for log base 5 of b. So we split things up. Log base 5, we've got multiplication not effectively, between each one of these. That's what it means when they're just stacked on top of each other. So log base 5 of 5 plus log base 5 of a plus log base 5 of b cubed. So log base 5 of 5 is just 1, because it's the same thing as its base and what it's being operating on. Plus log base 5 of a, we were told that was 6, so we get 6 plus, now log base 5 of b cubed, we can't do that yet. We need to get it as 5. But we know that we have to get it as just a b inside. But we see, oh, hey, there's an exponent. We can bring that out front. So we've got 3 times log base 5 of b. So now we can use the fact that it's 1.2. So 1 plus 6 is 7 plus 3 times 1.2, 1.2. 3 times 1.2 is 3.6. 7 plus 3.6 becomes 10.6. And there's our answer. Work on the other one, log base 25 of root a. So this is a kind of a problem, right? We've got 25 here, but we were told our base for working with this stuff, the information we're given was log base 5. So we have to use change of base. So now we see a time when you have to use change of base, not just for calculating numbers. So, if you have a calculator that can do change of base on its own that doesn't need you to do it, then there's still a use for it for problems like this. So change of base, we have that this log 25 of root a is the same thing as log of some base of root a divided by log of some base of what our original base was, 25. So what do we want to use there? Well, we probably want to use 5 because that's the thing we have all of our information on. So 5 and 5 here. So log base 5 of root a. Now, root a, that's not what we have. We have a. Is there another way to write root a that would involve a? Well, yeah, root a is the same thing as a to the 1/2. So we can write that as log 5 a to the 1/2 divided by log 5 of 25. Well, we see that log 5 squared, right? Because what number do you have to raise 5 to get 25? You have to raise it to 2. So at this point, 1/2 log 5 of a over 2 times log 5 of 5. Log 5 of 5 is just going to be 1. We swap out, we know that we've got 6 up here, so it's 1/2 times 6 divided by 2. 1/2 times 6 is equal to 3, still divided by 2. There we go. Cool. All right, final example, solve the following equations. So we didn't talk about how to solve equations like this very much in detail because hopefully this idea will make sense, but don't worry, we're going to talk about this in great detail in the next lesson where we'll really get into this, but we're just going to start off with some simple ones just in case you wind up having any problems like this already that you're working on. So solve the following equations. Log base 3 of x plus 5 equals 2. Now remember, we had that inverse property. We know that a to the log a of something winds up being equal to something because these cancel out. Now notice, we've got an equal sign here. So we know that log base 3 of x plus 5 is the same thing as 2. So we can use either one, either way we want to. So that means that a to the something equals a to something if it's the same somethings. So why don't we choose 3 as our a? So 3 to the stuff is equal to 3 to the stuff, as long as it's the same stuff. So let's put 2 over here and log base 3x plus 5 over here. So 3 squared and 3 to the log base 3 of x plus 5. So 3 and log 3, they wind up canceling out, and x plus 5 just kind of drops down. Equals, there's nothing to cancel on the right side, it's 3 squared, but we know what 3 squared is. 3 times 3 is 9. X plus 5 equals 9. We subtract by 5 on both sides, and we get x equals 4. Great. And if we wanted to, we could check that that does wind up working out. Check. We plug in our x equals 4, so log base 3 of 4 plus 5 equals 2. Does it? So log 3, 4 plus 5, let's see if that winds up coming out to be 2. Log 3 of 9. So what number do we have to raise 3 to get 9? We have to raise it to 2, so checks out. Great. E to the x minus 8 equals 47. So to do this one, we remember that log base a of a to the x equals x. So log on exponent, as long as they're exponentiation, as long as they're both the same base, also cancels out. So what is the base for e? That's natural log ln. We could also do log base e, but normally it's done as ln. So we can take the natural log of both sides. Just as we had 3 to the something equals 3 to the something, natural log of something equals natural log of something, as long as it's the same something. So natural log of stuff is equal to natural log of stuff, as long as it's the same stuff. Well, we've got this right here, so we know that 47 we can plug in over here, and e to the x minus 8 we can plug in over here because we are guaranteed by that equal sign that it's the same stuff on either side, that they wind up being the same thing. So natural log of e to the x minus 8, well, natural log is just log base e, so these cancel out and the x minus 8 drops down. And equals natural log of 47, well, that's going to wind up coming out to be a pretty not simple number. It's going to have a lot of decimals, so let's just leave it as natural log 47 for right now. And we wind up getting, by adding 8 to both sides, natural log of 47 plus 8. Now, alternatively, we could also figure out what this is as a decimal approximation. So if we punch natural log 47 into our calculator, we'd get, and then add 8 to it, we'd get approximately 11.85. So that would also be approximately 11.85. It is precisely natural log 47 plus 8, but if we want to take natural log 47, have a number that we can work with, it winds up coming out to something with a lot of decimals. It's just like when you've got, 2 times pi, you can leave the answer precisely as 2 times pi, but if you want to, you can also approximate that into 6.28, and then there's also stuff to it, right? So 2 times pi is the exact answer, but you also might want a decimal answer to work with, so you can approximate it by multiplying it out. Natural log 47, same sort of thing as in the pi example. It's something that is a complicated number, so we might want to leave it precisely, or we might want to get it approximately. We can check with this number, and we have that e to the, let's use our decimal approximation so we can actually put it into a calculator. E to the 11.85 minus 8. What do we put that in? So that will become e to the 3.85. E to the 3.85 winds up being approximately 46.99. So that winds up checking out because ultimately, remember, we just said it was an approximation, not perfectly the answer. The thing that is perfectly the answer is this one right here. Pretty great stuff, allows us to get a whole bunch of applications worked out with this, as we'll see in 2 lessons from now when we talk about applications of this stuff. And in the next lesson, we'll really dive into how do we solve equations like this. So if you want more information on that, check out the next lesson where we'll really see some really complicated examples, get a really great idea of how this stuff works, and we'll really understand how to solve all these sorts of equations. All right, we'll see you at educator.com later. Bye.